Hello sir, I'm Hardik Setta and my topic is error detection and correction. Okay, so let's get some overview about our topic. Introduction. In networks must be able to transfer data from one device to another with acceptable accuracy. All error detection and correction schemes add some redundancy or some extra data to a message which receivers can use to check consistency of the delivered message and to recover data that has been determined to be corrupted. Wait, so why should we need this thing? Because of data can be corrupted during transmission. Some applications requires that error be detected and corrected, but some application can tolerate a small level of error. For example, random errors in audio or video transmission may be tolerable, but when we transfer text, we expect a very high level of accuracy. So first of all, we are aware about position of the data link layer. Okay, wait a second. Sure, basically the data link layer is the second layer in the OSI model. The three main functions of the data link layer are to deal with transmission errors, regulate the flow of data, and provide a well-defined interface to the network layer. So this is our error control. This is our main part of error detection and correction parts in data link layer. So okay, so let's move. Types of errors. There are two types of errors: single bit error and burst error. Okay. Single bit error. In a single bit error, only one bit in the data unit has changed. Imagine that each group of 8 bits in n ASCII character with a 0 bit added to the left. Okay, so now I'm showing you. Uh, okay, so in the figure we have 0 0 0 0 0 0 0 1 0 was sent, meaning start of text, but the 0 0 0 0 1 0 1 0 was received, meaning line feed. So here single bit errors are the least likely type of error in serial data transmission. To understand why, imagine data sent at 1 Mbps for a single bit error to occur. The noise must have a duration of only 1 microsecond, which is a very rare noisy normally lasts much longer than this. Okay, so second one is burst error. A burst error means that two or more bits in the data unit have changed. Okay, so here our 16 bits sent and received 16 bit. So here figure shows the effect of a burst error on a data unit. In this case, we sent our this 16 bit and received our this 16 bit. A burst error is more likely to occur than a single bit error. So here showing that we sent a length of 5 bits errors, burst errors. So 0 to 1, 0 to 1, 0 to 1 because of our corrupted by burst error. So the duration of noisy is normally longer than the duration of one bit, which means that when noise affects data, it affects a set of bits. For example, if we are sending data at 1 kbps, a noise of 1100 can affect 10 bits. If we are sending data at 1 mbps, the same noise can affect 10,000 bits. Okay, let's move on. Error detection. Basically, error detection uses the concept of redundancy, which means adding extra bits for detecting errors at the destination. Okay, let's move on. Redundancy. To detect or correct errors, we need to send extra or say redundant bits with data. So these extra bits are added by the sender and removed by the receiver. Their presence allows the receiver to detect or correct corrupted bits. Redundancy is achieved through various coding schemes. The sender adds redundant bits through a process that creates a relationship between the redundant bits and the actual data bits. The receiver checks the relationship between the two sets of bits to detect or correct the errors. The ratio of redundant bits to the data bits and the robustness of the process are important factors in any coding scheme. Here the figure shows the general idea of coding. Detection methods. There are three types of methods. First, parity check, second, cyclic redundancy check, and third, checksum. So let's see first method. Parity check. A parity bit is added to every data unit so that the total number of firsts becomes even for even parity check or odd for odd parity check. So what is simple bit parity check? A simple bit parity check code is a single bit error detecting code in which n is equal to k plus 1 with d minimum is equal to 2. The extra bit called the parity bit is selected to make the total number of is in the code word even. Although some implementation specify an odd number of is, we discuss the even case. Okay, two-dimensional parity check. Now let us discuss a category of error correcting codes called Hamming codes. These codes were originally designed with d minimum is equal to 3, which means that they can detect up to 2 errors or correct one single error. Although there are some Hamming codes that can correct more than one error, or discussion focus on the single bit error correcting code. So let's take one example. So now we are getting 5 blocks centered, and however it is hit by a burst noise of length 8 and some bits are corrupted. So we showing that here first block our has a 0011 and our second block changed by burst noise for 1000, and so that when the receiver checks the parity bits, some of the bits do not follow the even parity rule and the whole block is discarded. So here showing our last block, fifth block are not changed. So this is a one type of effect. Cyclic redundancy check. In cyclic codes are special linear blocks codes with one extra property. In a cyclic code, if a code word is cyclic shifted, the result is another code word. For example, if we have 1011000 is a code word and we cyclically left shift, then the bit is C01100001 is also a code word. Okay, let's move on. Revision in CRC encoder. So let's showing that. Okay. In each step, a copy of the divisor is XORed with the 4 bits of the dividend. So the result of the XOR operation is 3 bit. So we're getting our 3 bits, which is used for the next step after one extra bit is pulled down to make it 4 bits longer. So there is one important point we need to remember in this type of revision, that if the leftmost bit of the dividend is 0, the step cannot use the regular divisioner. We need to use an all OS divider. Okay. Division in CRC encoder. So the code word can change during transmission. The decoder does the same division process as the encoder. So we have here data, and the remainder of the division is the syndrome. So if the syndrome is all zeros, there is no error. The data word is separated from the received code word and accepted, otherwise everything is discarded. Figure shows two cases. The left-handed figure shows the value of syndrome. When no errors has occurred, the syndrome is 00. The right-handed part of the figure shows that case in which there is one single error. Syndrome is not all zeros. Polynomials. A better way to understand cyclic codes and how they can be analyzed is to represent them as polynomial. A pattern of zeros and ones can be represented as a polynomial with coefficients of 0 and 1. Figure shows a binary pattern and its polynomial representation. In figure, we show how to translate a binary pattern to a polynomial. We show how to polynomial can be shortened by removing all terms with 0 coefficients and replacing x1 by x and x0 by 1. Okay, let's move on. Checksum. The last error detection method we discussed here is called the checksum. The checksum is used in the internet by several protocols, although not at the data link layer. It is used by the higher layer protocols, and it is based on the concept of redundancy like VRC, LRC and CRC. Okay, let's move on. So this is some steps of checksum, and it's called a checksum generator, and let's following steps of sender does. The unit is divided into case section, each of n bits. Section 1 and 2 are added together using 1's complement. Section 3 is added to the result of the previous step. Section 4 is added to the result of the previous step, and the process repeats until the section K is added to the result of the previous step. The final result is complemented to make the checksum. Okay. Internet checksum. So traditionally the internet has been using a 16-bit checksum. The sender and receiver calculates the checksum by following these steps. Sender side. First, the message is divided into 16-bit words. The value of the checksum word is set to 0. All words including the checksum are added using 1's complement additions. The checksum is completed and becomes the checksum. Fifth, the checksum is sent with the data. At the receiver side, first the message including checksum is divided into 16-bit words. Second, all words are added using 1's complement additions. Third, the sum is complemented and becomes the new checksum. Fourth, if the value of checksum is 0, the message is accepted, otherwise it is rejected. Okay, let's move on. So we are reaching our second main part, error corrections. So it can be handled in two ways. First, when an error is discovered, the receiver can have the sender retransmit the entire data unit. Second, a receiver can use an error correcting code which automatically corrects certain errors. Okay. Single bit error correction. Parity bits. The secret of error correction is to locate the invalid bit or bits. For ASCII code, it needs a 3-bit redundancy code 000 and 111. Okay. Redundancy bits. So here figure showing that the calculated the number of redundancy bit required to correct a given number of data bit. The next slide is relationship between data and redundancy bits. So you're showing that number of data bits, number of redundancy bits and total bits. Let's move on. Hamming codes. So here figure showing that position of redundancy bits in Hamming code. So we put redundancy bits in our bits, and each R bit is the VRC bit for one combination of data bits. So here R1 bits is have 1, 3, 5, 7, 9, 11. R2 bits have 2, 3, 6, 7, 10, 11. R4 bits have 4, 5, 6, 7, and R8 bits have 8, 9, 10, 11. Multiple bit error correction. So redundancy bits calculate one overlapping sets of data units can also be used to correct multiple bit errors. Example, to correct double bit error, we must take into consideration that two bits can be combination of any two bits in the entire sequence. So now we are reach our conclusion that error correction codes are a mean of including redundancy in a stream of information bits to allow the detections and correction of symbol errors during transmission. Thank you. Thanks for watching.